Good evening, and welcome to The Gentle Scientist. Tonight, we drift backward through the mists of deep time to an age when the earth trembled beneath footsteps larger than houses, when the skies rang with calls no human ear has ever heard, when giants walked, flew, and ruled a world utterly unlike our own. For more than 165 million years, dinosaurs shaped the continents, carved paths through ancient forests, and left their marks in stone that would sleep in darkness for tens of millions of years more. They lived through climates we can barely imagine, survived catastrophes that reshaped the planet, and evolved into forms so diverse, so strange, so magnificent that even now we struggle to comprehend their reality. Tonight, we will trace their beginning from the ashes of extinction, watch them grow from small, quick creatures into the largest land animals ever to exist. We will hear the echoes of ancient calls and witness the final day when fire fell from the sky and changed everything forever. Along the way, you will learn secrets preserved in stone, colors lost for 66 million years now recovered, and behaviors written in fossilized footprints that tell stories of care, cooperation, and survival. Each fact is a doorway. Each discovery is a whisper from a vanished world that refuses to be forgotten. If you enjoy these quiet journeys through science and time, I invite you to hit the like button, subscribe to The Gentle Scientist, and share your thoughts below, or just comment where you are listening from. This helps others find their way here too, one curious soul at a time, one peaceful night at a time. For now, just breathe. Let your shoulders soften. Let the weight of the day settle away. Close your eyes if you wish. We are about to step across a threshold that spans millions upon millions of years, to a time before humans, before mammals ruled the earth, before flowers painted the world in color, a time when the planet belonged to creatures both terrifying and beautiful, both alien and strangely familiar. Now, let's begin. The story of the dinosaurs begins with silence, with ash settling over a world that had nearly died. Around 252 million years ago, the Earth endured what scientists call the Permian-Triassic extinction, the most devastating loss of life our planet has ever known. Volcanic eruptions on a scale beyond imagination darkened the skies. Oceans turned acidic and oxygen-starved. More than 90% of all species vanished, their existence erased thoroughly. For millions of years afterward, the world lay quiet, wounded, struggling to recover. The few survivors clung to life in a landscape of ash and stone. But life, as it always does, found a way forward. Slowly, ecosystems began to rebuild. Ferns carpeted the barren ground. Small reptiles emerged from shelter, and in this emptied world, evolution had space to try new forms. The first dinosaurs appeared during the Middle Triassic period, roughly 230 million years ago. They were not giants. They were not the rulers of anything. These earliest dinosaurs were small, perhaps the size of a modern dog or turkey, moving on two legs with a speed and agility that set them apart. Their hind limbs were positioned directly beneath their bodies, not sprawled to the sides like most reptiles. This simple difference, this shift in posture, gave them an advantage in a world where speed and endurance mattered. Lightweight frames, quick movements, alert eyes, scanning a landscape still recovering from catastrophe. They lived in the shadow of other reptiles, creatures called archosaurs that had diversified into many forms. Some of these relatives would become crocodiles. Others would evolve into pterosaurs and take to the skies. The early dinosaurs occupied their own branch of this family tree, unremarkable at first, just another experiment in survival. The world they lived was strange and unfamiliar. All the continents were joined into a single supercontinent called Pangaea, a vast landmass stretching from pole to pole. The interior of Pangaea was dry, scorching, a desert larger than any that exists today. Monsoons drenched the coasts seasonally, but the heart of the land baked under a relentless sun. There were no flowers yet, no grass, no birds singing in the trees. The forests were made of conifers, cycads, and ferns. The soundtrack was the hiss of wind through primitive plants and the calls of creatures we would barely recognize. In this world, dinosaurs were not alone. They shared the land with other reptiles that seemed more likely to inherit the earth. Massive predators called Rauisuchians stalked the same prey. Herbivorous rhynchosaurs grazed in herds. Early mammal relatives, small and nocturnal, hid in the undergrowth. For 20 million years, dinosaurs remained a relatively minor part of the ecosystem. One group among many. Nothing special, nothing dominant. But evolution works in currents too slow to see, in adaptations tested across generations, in advantages so subtle they only reveal themselves over millions of years. The dinosaurs possessed traits that would eventually tip the balance in their favor. Their upright posture meant they could move efficiently over long distances. Their hip and leg structure allowed both speed and stamina. Many developed hollow spaces in their bones, making them lighter without sacrificing strength. These innovations, small on their own, combined into something powerful. Then, around 201 million years ago, the world convulsed again. The Triassic period ended with another mass extinction, smaller than the one before, but devastating nonetheless. Volcanic eruptions split Pangaea apart, releasing gases that poisoned the air and warmed the planet. Many of the large predators that had kept dinosaurs in check disappeared. The Rauisuchians vanished. Other competing reptile groups dwindled. In the aftermath, the ecological stage lay open once more. This time, the dinosaurs walked onto it and stayed. The Jurassic period dawned with dinosaurs spreading across the fragmenting continents. They diversified rapidly, adapting to new environments, growing larger, more varied, more successful. Some became swift hunters. Others evolved into massive herbivores that could reach the highest branches. Still others developed armor, spikes, and defensive weapons beyond anything seen before. What began as a quiet emergence in the shadow of greater creatures had become a dynasty. The age of dinosaurs had truly begun, and it would last for more than 135 million years. To put that in perspective, humans have existed for perhaps 300,000 years. Our entire species story could repeat itself more than 450 times within the span of dinosaur dominance. They were not a brief experiment. They were the most successful large land animals in Earth's history. As the Jurassic gave way to the Cretaceous, dinosaurs continued to evolve and diversify. They adapted to every environment, from lush river valleys to arid plains, from dense forests to open coastlines. They evolved complex social behaviors, developed elaborate display structures, and some even began growing feathers, setting the stage for a revolution that would eventually lead to flight. The small, quick creatures of the Triassic had become the architects of entire ecosystems. Standing in the fossil halls of museums today, looking up at the towering skeletons, it is easy to forget that these giants had humble beginnings, that they emerged not through sudden conquest, but through persistence, through surviving when others fell, through small advantages accumulated over unfathomable stretches of time. There is a paradox written in stone across every continent, a puzzle that challenged scientists for more than a century. How could animals grow so impossibly large? How could creatures weighing as much as 10 elephants stand upright, walk, feed, and thrive for millions of years without collapsing under their own mass? The sauropods, those long-necked giants that moved like living mountains across the Mesozoic world, should not exist. And yet they did. Argentinosaurus, Patagotitan, Brachiosaurus, Diplodocus. Names that evoke wonder even before you see their skeletons. Some exceeded 100 feet in length. Some stood 6 stories tall. Some weighed 70 tons or more, heavier than any land animal that came before or after. When paleontologists first assembled their bones, the sheer scale seemed impossible. Surely these creatures spent their lives in water, buoyed by lakes and rivers. Surely their legs could not support such weight on land alone. But the fossils told a different story. Footprints preserved in ancient stone showed they walked on solid ground, their massive feet leaving impressions deep in mud that would harden into permanent testimony. The structure of their limbs revealed weight-bearing adaptations, pillar-like legs positioned directly beneath their bodies, not sprawled like lizards, but columnar like elephants, only far more massive. The secret of their size begins with hollow bones. When you examine a sauropod vertebra, you discover it is not solid stone-like density all the way through. Instead, the bones are filled with air spaces, pockets, and chambers that reduced weight without sacrificing strength. This innovation, this pneumatization of the skeleton, was borrowed from an ancient lineage and refined over millions of years. Birds possess it today, their hollow bones allowing flight. In dinosaurs, it allowed enormity. These air sacs extended beyond the bones themselves, creating a system of internal airflow that connected to the lungs. Imagine a network of balloons threaded through the skeleton, inflating spaces within vertebrae, ribs, and even some limb bones. This respiratory system was remarkably efficient, allowing sauropods to extract more oxygen from each breath than mammals can. With every inhalation, air flowed through the lungs and into these sacs, and with every exhalation, that air passed through the lungs again, maximizing oxygen absorption. A continuous, one-way flow of air through the respiratory system, even while breathing in and out. This efficient breathing was crucial because size creates problems. As an animal grows larger, its volume increases faster than its surface area. A sauropod's massive body generated enormous heat from muscle activity and digestion. but it had relatively little skin surface through which to release that heat. The air sac system helped. Cool air flowing through the body acted as an internal cooling mechanism, preventing overheating in creatures that could not sweat, could not pant effectively, and lived in climates often warmer than today's. But breathing was only part of the puzzle. Consider the heart. A brachiosaurus stood perhaps 40 feet tall at the head. Its heart had to pump blood up that impossibly long neck against gravity's pull, delivering oxygen to a brain-positioned stories above the chest. The blood pressure required for this feat would rupture the vessels of any mammal. Yet sauropods managed it through adaptations we are still working to understand fully. Likely, their hearts were enormous, powerful, perhaps weighing a ton or more, beating slowly but with tremendous force. The blood vessels in their necks may have contained valves to prevent backflow, and the skin around their necks might have been tight, acting like compression stockings to assist circulation. The neck itself is a marvel of engineering. Stretching 30, 40, even 50 feet in some species, composed of vertebrae elongated beyond anything seen in other animals, lightweight yet strong enough to support the weight of the head and withstand the constant force of gravity. Some sauropods had necks with 15 vertebrae, others had 19. Each bone was hollowed by those air sacs. Each was shaped to interlock with its neighbors, creating a flexible column that could sweep across wide arcs, reaching vegetation other herbivores could not touch. For decades, scientists debated how sauropods held these necks. Early reconstructions showed them rearing up like swans, heads held high, feeding on treetops. Later analysis suggested they held them more horizontally, sweeping side to side across low vegetation like living vacuum cleaners. The truth, revealed through careful study of bone structure and muscle attachment points, is probably somewhere between. Different species likely held their necks at different angles, some habitually browsing low, others capable of rearing up to reach higher. The flexibility allowed them to exploit food sources across multiple levels of the forest, from ground cover to canopy. That neck served another purpose beyond feeding. It was a counterbalance. At the other end of the body stretched a tail equally long, equally massive, a muscular whip that could contain 50 or more vertebrae. The tail balanced the neck. The hips sat at the center of gravity. When a sauropod walked, it was fundamentally a four-legged creature, but one designed around a horizontal axis, weight distributed carefully between front and back. The tail dragged the ground in early reconstructions, leaving furrows in the mud. Modern understanding suggests they held their tails aloft, using them for balance, possibly for defense, perhaps even for communication, cracking them like whips to produce sounds that rolled across the landscape. The legs beneath this mass were pillars of bone, solid and straight, each one thicker than a tree trunk. The femur of a large sauropod could measure 8 feet long and weigh more than a horse. These bones were dense, not hollowed like the vertebrae, because they had to bear weight. The feet were broad, spreading the load across padded soles, some species walking on their toes like elephants, others more flat-footed. Trackways show they moved in herds, adults and juveniles together, sometimes following the same paths year after year, wearing trails into ancient stone. How fast could they move? Not quickly by our standards, but faster than you might expect for something so large. Estimates suggest adults could walk at perhaps 4 to 5 miles per hour, a steady, ground-shaking plod. Juveniles were likely quicker, more agile, staying close to the protection of the herd. The physics of their stride, the leverage of those immense limbs, meant each step covered tremendous distance. They did not need speed. Their size was their defense. But size creates another challenge. Food, a 70-ton animal, requires enormous amounts of energy to maintain. Sauropods were herbivores, feeding on plants that are far less energy dense than meat. Calculations suggest a large sauropod needed to consume hundreds of pounds of vegetation daily, perhaps more than half a ton. They could not chew. Their teeth were simple, peg-like or spoon-shaped, designed for stripping and cropping, not grinding. Food went into the stomach whole or in large pieces. Here, another adaptation emerged. Gastroliths, stomach stones. Sauropods deliberately swallowed rocks, smooth stones that tumbled in their massive guts, grinding plant matter like a living mill. When paleontologists find sauropod fossils, they sometimes discover piles of polished stones in the rib cage area, stones from miles away, carried within the animal as tools for digestion. As the stones wore smooth, the dinosaurs would regurgitate them and swallow new, rougher ones. A simple solution to the problem of breaking down tough plant fiber without teeth capable of chewing. Their digestive systems were enormous. Fermentation chambers where bacteria broke down cellulose over days or weeks. Like modern cows, they likely belched prodigious amounts of methane, contributing to the atmospheric composition of their time. Some scientists have suggested that during the Mesozoic, when sauropods were abundant, their collective emissions may have influenced global climate, adding warmth to an already warm world. The sauropods prove that evolution has no ceiling, no size limit beyond the constraints of physics and biology themselves. They pushed those constraints to the absolute edge and survived there for epochs. They show us that the familiar is not inevitable, that life can take forms we might think impossible, that the ancient earth was capable of producing wonders that dwarf anything alive today. While dinosaurs claimed the land, the skies belonged to their cousins. The Mesozoic skies were ruled by creatures stranger and more magnificent than any flying animal alive today. Pterosaurs, winged reptiles that soared above the heads of dinosaurs for more than 150 million years, masters of an element their earthbound relatives could only dream of reaching. It is important to understand what pterosaurs were not. They were not dinosaurs, though they shared a common ancestor with them. They were not birds, though they conquered flight millions of years before birds existed. They were their own lineage, a parallel experiment in powered flight, an evolutionary path that arose in the Triassic and endured until the very end of the Cretaceous. They were reptiles that learned to fly, and in doing so, they transformed the ancient world. The earliest pterosaurs appeared around 220 million years ago, small creatures with wingspans measured in inches, delicate frames lifted by membranes of skin stretched between impossibly elongated fourth fingers and their bodies. Imagine holding your hand before you and watching one finger grow, extend, reach outward until it is 3 times the length of your entire arm. That finger becomes the leading edge of a wing, and from it stretches a membrane thin as silk, but strong as leather, catching air, generating lift, allowing a reptile to leave the ground behind. These pioneers were no larger than sparrows, darting through Triassic forests, snatching insects from the air with needle-sharp teeth. Their hollow bones, inherited from their archosaur lineage, made them light enough to fly. Their large eyes gave them keen vision for tracking prey. Their flexible necks allowed them to strike at moving targets. They were predators of the air, filling a niche that existed in emptiness, hunting in 3 dimensions while dinosaurs were still learning to walk. But size, in pterosaurs, was not fixed. Evolution pushed them in directions that still challenge our understanding of flight. Over millions of years, some lineages grew larger, and larger, and larger still. By the late Cretaceous, pterosaurs had achieved sizes that seemed to mock the laws of aerodynamics. Quetzalcoatlus, named for the Aztec feathered serpent god, stood as tall as a giraffe when folded on the ground. Its wingspan reached 35 feet or more, wider than a small airplane, wider than any bird that has ever existed. How could something so enormous fly? The question haunted scientists for decades. Early estimates suggested Quetzalcoatlus might weigh 500 pounds or more, far too heavy for its wings to lift. But careful analysis revealed the truth. Despite its size, it weighed perhaps 200 to 250 pounds, no heavier than a large human. Every bone was hollow, some with walls thinner than paper. The wing membrane itself was reinforced with structural fibers, like natural cables running through the skin, providing strength without adding weight. The entire animal was an exercise in minimalism, mass reduced to the absolute minimum necessary for structure, everything else sacrificed to the demands of flight. The wings themselves were marvels of biological engineering. Unlike bird wings, which are made of feathers attached to modified arms, pterosaur wings were continuous membranes. The leading edge ran along that elongated fourth finger, the trailing edge attached to the body and likely connected to the hind limbs, though scientists still debate exactly where. Some species had short, broad wings for maneuverability. Others had long, narrow wings for soaring. Each design reflected a different lifestyle, a different way of extracting energy from the air. Flight requires more than wings. It requires power. Pterosaurs possessed massive chest muscles anchored to a keeled breastbone, similar to birds. These muscles powered the downstroke, driving the wings through air, generating thrust and lift. Computer models suggest they were capable flyers, not clumsy gliders barely staying aloft, but agile, efficient, capable of powered flight over long distances. Trackways preserved in ancient mud show them walking on all fours when grounded, wings folded, moving with an awkward but functional gait, launching themselves into the air with powerful leaps assisted by their wing muscles. The diversity among pterosaurs is staggering. At one end of the spectrum, tiny Anurognathes, no larger than a butterfly, hunted insects at dusk with a wide mouth and excellent low-light vision. At the other end, the giant Ozdarkids like Quetzalcoatlus stalked across floodplains, terrestrial hunters when not flying, using their long necks and sharp beaks to snatch prey from the ground. Perhaps fish from shallow waters, perhaps small dinosaurs, perhaps carrion. Between these extremes existed hundreds of species, each adapted to different food sources, different environments, different strategies for survival. Some pterosaurs developed elaborate head crests, bony structures extending backward from their skulls, covered in keratin sheaths shaped like sails, hammers, spears, or crowns. For years, scientists puzzled over these crests. They seemed impractical, adding weight and wind resistance. But studies revealed they served multiple purposes. Some species use them as rudders during flight, improving control and stability. Others use them for display, signaling to mates and rivals, identifying species and individuals. Crests could be brightly colored, adorned with patterns, shaped by sexual selection as much as aerodynamics. Evidence suggests pterosaurs were covered in a fuzzy coating, thin filaments called pycnofibers that resembled fur or primitive feathers. These structures provided insulation, suggesting pterosaurs were warm-blooded, maintaining high body temperatures necessary for the energetic demands of flight. Fossilized skin impressions show the wing membranes were complex structures containing layers of different tissues, blood vessels for nourishment and thermoregulation, and muscular fibers that allowed the wings to change shape during flight, adjusting camber and angle to suit different flying conditions. They nested in colonies, some species laying eggs in cliff faces, others on beaches, still others in trees. Fossil discoveries have revealed eggs with leathery shells, embryos preserved in exquisite detail, even newly hatched young. Remarkably, baby pterosaurs appear to have been capable of flight almost immediately after hatching, precocial flyers born with wings already functional. This is unlike modern birds, which require weeks or months of growth before flying. Young pterosaurs had proportionally larger wings than adults, allowing them to fly despite their underdeveloped muscles. As they grew, their wings caught up with their bodies, and they gradually developed the power needed for adult flight. The skies of the Mesozoic must have been crowded. Small insectivores hunted at dawn and dusk. Fish eaters soared over oceans and rivers, plunging into water with specialized beaks. Terrestrial hunters stalked across plains, shadows crossing the ground like silent omens. Some migrated across vast distances, following seasonal resources. Others stayed local, defending territories from cliffs or tall trees. This aerial world endured for more than 150 million years. Pterosaurs outlasted entire orders of dinosaurs. They survived mass extinctions. They adapted to changing climates, shifting continents, evolving competitors. They witnessed the rise of birds, those feathered dinosaurs that took to the skies alongside them. And for tens of millions of years, the two groups shared the air, pterosaurs and birds coexisting, each successful in their own right. But pterosaurs faced challenges that perhaps made them vulnerable. Their lightweight skeletons, so perfect for flight, were fragile. Injury meant death. Their eggs, though leathery, were exposed. Their young, though capable of early flight, were small and vulnerable to predators. Unlike birds, which could diversify into many sizes, including tiny forms that required little food, most pterosaurs remained medium to large, requiring substantial resources. As the Cretaceous progressed, competition increased. Birds diversified rapidly, becoming more numerous. The ecological space for pterosaurs may have narrowed. And then came the end. 66 million years ago, when the asteroid struck and the world convulsed into darkness and winter, the pterosaurs vanished completely. Not a single lineage survived. While some birds made it through, finding shelter, surviving on seeds and small prey, the pterosaurs disappeared as thoroughly as the non-avian dinosaurs. Perhaps their size worked against them in the aftermath. Perhaps the collapse of ecosystems eliminated their food sources too quickly. Perhaps the loss of flight ability in harsh conditions meant death. Their extinction remains mysterious in its completeness, but their legacy endures in stone. Thousands of fossils from sites around the world preserve their forms in exquisite detail. The Solnhofen limestone of Germany captures them mid-flight, wings spread, every bone visible. The rocks of Brazil reveal soft tissues, membranes, even internal organs. Chinese deposits yield feathered or furred specimens, showing the pycnofibers that covered them. Each discovery refines our understanding, adding detail to the picture of these remarkable creatures. Pterosaurs remind us that flight, that miracle of leaving the ground, has evolved independently multiple times in Earth's history. Insects achieved it first. Pterosaurs came second, birds third, bats fourth. Each time, life solved the same problem in different ways, using different structures, different mechanics, different strategies. The pterosaur solution, that membrane wing stretched on an elongated finger, worked brilliantly for longer than most animal groups exist at all. While dinosaurs claimed the land and pterosaurs owned the skies, the oceans of the Mesozoic belonged to creatures equally magnificent and equally strange. Not dinosaurs, though they lived alongside them, sharing the same world, breathing the same air when they surfaced, witnessing the same sunrises over coastlines that have long since vanished. These were marine reptiles, descendants of land-dwelling ancestors who had made the extraordinary journey back into the sea, trading legs for flippers, lungs adapted for air for bodies shaped by water, returning to the element from which all life originally came. The story of marine reptiles is one of convergent evolution, of life solving the same problems in similar ways across millions of years. Long before dolphins and whales evolved from land mammals, long before seals and sea lions adapted to ocean hunting, reptiles made that transition, and they did it multiple times, in multiple lineages, each one independently discovering how to transform a body built for walking into one suited for swimming. The solutions they found, the shapes they took, would be echoed millions of years later when mammals followed the same path back to the sea. The earliest marine reptiles appeared in the Triassic, not long after the Permian extinction had emptied the oceans of most large predators. The ichthyosaurs were among the first, and eventually among the most specialized. Their name means fish lizard, and the name is apt. Through millions of years of evolution, they came to resemble fish more than reptiles. Their bodies streamlined into perfect torpedo shapes, their limbs transformed into steering fins, their tails developing flukes for propulsion. If you saw an ichthyosaur in silhouette, you might mistake it for a dolphin. The resemblance is uncanny, not because they were related, but because the ocean demands certain forms from anything that wants to move through it efficiently. Both needed streamlined bodies to reduce drag. Both needed powerful tails for propulsion. Both needed fins for steering and stability. The ocean is a strict teacher, and it teaches the same lessons to all its students, regardless of their ancestry. Ichthyosaurs learned those lessons so well that they became some of the fastest predators in Mesozoic seas. The largest ichthyosaurs rivaled modern sperm whales in size, reaching lengths of 60 feet or more, though most species were smaller, perhaps 6 to 12 feet long. Swift hunters of fish and squid in warm, shallow seas. Their eyes were enormous, the largest eyes relative to body size of any vertebrate ever discovered, some as large as dinner plates. These massive eyes suggest they hunted in deep water or at night, where light was scarce and vision needed every advantage. The ocean was darker then, the water thick with life, and those huge eyes pulled in every photon, every glimmer of bioluminescence, every shadow that might be prey. Remarkably, we know ichthyosaurs gave birth to live young rather than laying eggs. Fossils have been found with babies preserved inside the body cavity, and some even capture the moment of birth, a juvenile emerging tail first, just as modern dolphins and whales are born, an adaptation preventing drowning during delivery. These fossils, found in Germany's Poseidonia Shale and other sites, are among the most poignant in paleontology. Mothers and babies frozen together in the moment of life becoming death, preserved for 180 million years in stone that formed from the sea floor mud that entombed them. The plesiosaurs took a different approach to marine life. Rather than becoming fish-like, they developed a body plan unlike anything else that has ever existed. Imagine a barrel-shaped body, 4 large flippers, and a neck that could be short and thick or impossibly long and serpentine depending on the species. Some plesiosaurs had necks containing more than 70 vertebrae, necks longer than their entire body, necks they could curve and twist with remarkable flexibility, snaking through the water in search of prey. These long-necked varieties, called elasmosaurs, looked like something from mythology when they swam, their necks breaking the surface far from their bodies, leading ancient sailors who might have glimpsed them to tell tales of sea serpents. They could reach 40 feet in length, though much of that was neck and tail, the body itself remaining relatively modest. How they hunted with such necks remains debated. The neck was powerful, but not particularly fast, unsuited for chasing swift fish. More likely, they used stealth. The small head at the end of that long neck, approaching schools of fish from unexpected angles. The body remaining still, while the neck did all the work. Shorter-necked plesiosaurs, the pliosaurs, were the apex predators of Mesozoic oceans. They sacrificed neck length for massive heads and powerful jaws, becoming the oceanic equivalent of tyrannosaurs. Predator X, a pliosaur discovered in Norway, had a skull nearly 10 feet long, jaws lined with teeth the size of cucumbers, a bite force that could crush bones and shells with ease. These creatures hunted other marine reptiles, large fish, anything they could overpower. They were patient predators, using their 4 flippers to maneuver with surprising agility for their size, hanging motionless in the water column before striking with explosive speed. The flippers themselves were marvels of adaptation. Unlike fish fins, which are supported by rays of bone or cartilage, plesiosaur flippers were modified limbs, each containing the same bones as a land animal's leg, but elongated, flattened, and arranged into a structure that functioned like wings underwater. They flew through the ocean, their swimming motion more like bird flight than fish swimming, the flippers providing both propulsion and steering, allowing tight turns and rapid acceleration despite their large size. By the late Cretaceous, a new group of marine reptiles had evolved to dominate the seas, the mosasaurs. These were the last and perhaps most successful of the marine reptiles, appearing relatively late in the Mesozoic, but spreading rapidly across every ocean. They were descended from land-dwelling monitor lizards, relatives of modern Komodo dragons, and retained more of their terrestrial ancestry than ichthyosaurs or plesiosaurs. Their bodies were elongated and flexible, powered by long tails that undulated side to side like crocodiles. Their limbs transformed into flippers, but still recognizably leg-like in structure. Mosasaurs came in many sizes, from species barely larger than a human to giants like Mosasaurus hoffmanii, which could exceed 50 feet in length and weigh 15 tons. They had double-hinged jaws that could open extraordinarily wide, allowing them to swallow large prey whole, and their teeth curved backward, preventing escape once something was caught. Stomach contents, preserved in some fossils, reveal they ate fish, sea turtles, other marine reptiles, even seabirds unfortunate enough to land on the water's surface within reach. The spread of mosasaurs was explosive by geological standards. Within 10 million years of their appearance, they had diversified into dozens of species adapted to different hunting strategies, different prey. Some had blunt crushing teeth for eating shellfish and ammonites. Others had slender snouts for catching fish. Still others were generalists, opportunistic predators that ate whatever they could catch. They filled the role that sharks play in modern oceans, the primary predators, the creatures other animals watched for, the shapes that created fear when they appeared from the depths. The oceans these reptiles inhabited were warmer than today's seas, greenhouse climates, keeping even polar waters temperate, allowing marine reptiles to range across the entire globe. Shallow seas covered much of the continents, creating vast inland seaways like the Western Interior Seaway that split North America in half, connecting the Gulf of Mexico to the Arctic Ocean. These shallow seas were incredibly productive, teeming with fish, ammonites, belemnites, the coiled and straight-shelled cephalopods that served as primary prey for many marine predators. The seafloor of these ancient oceans is now exposed as land, and within the rocks that form from those sediments lie the fossils of marine reptiles in extraordinary abundance and preservation. The chalk deposits of Kansas, once the floor of the Western Interior Seaway, yield mosasaur skeletons so complete that every bone remains in position, some even preserving traces of soft tissue, outlines of flippers, impressions of scales. The shales of Germany produce ichthyosaurs that died and sank into anoxic bottom waters where decay slowed to almost nothing, preserving details of skin, muscle, even stomach contents showing their last meals. These fossils reveal not just anatomy, but behavior. Bite marks on bones show predation and scavenging. Mosasaurs feeding on plesiosaurs. Larger mosasaurs cannibalizing smaller ones. Sharks scavenging anything dead that sank within reach. Healed injuries show survival. Creatures that were bitten or struck by predators but escaped and lived long enough for bones to mend. Some fossils show evidence of infection, of bones damaged by disease, of parasites that burrowed into skulls or nested in body cavities. The world of Mesozoic oceans was interconnected with the land in ways that modern oceans are not. Sea turtles, descended from land-dwelling ancestors, laid eggs on beaches alongside dinosaurs. Flying pterosaurs hunted fish in the same waters where mosasaurs lurked below. Dinosaurs walked along coastlines and occasionally waded into shallow water, their footprints preserved in coastal sediments, sometimes showing where they swam briefly before returning to land. The boundary between terrestrial and marine was porous, crossed regularly by creatures adapted to both. Marine reptiles themselves likely came ashore, at least occasionally. Most probably gave birth in the water, like ichthyosaurs, but some may have hauled themselves onto beaches to lay eggs, a risky venture for animals so well adapted to water, their weight barely supported by flippers designed for swimming. No definitive evidence of this behavior exists, but the evolutionary history suggests it may have occurred in some lineages, echoes of their terrestrial origins compelling them to return to land at least for reproduction. The extinction that ended the dinosaurs ended the marine reptiles too. Mosasaurs, plesiosaurs, and the few remaining ichthyosaurs all vanished in the aftermath of the asteroid impact. The oceans, already stressed by volcanic activity and changing climates, were devastated by the impact's effects. Tsunamis scoured coastlines. Acid rain poisoned surface waters. The collapse of plankton populations eliminated the base of the food chain. Darkness prevented photosynthesis. Within years, perhaps decades at most, the great marine reptiles had disappeared as completely as the dinosaurs on land. Unlike dinosaurs, marine reptiles left no descendants. No lineage survived to carry their genetics forward. When they died completely. Every species, every genus, every family. The oceans were emptied of large predators, and into that emptiness moved other creatures. Sharks, which had survived every extinction event for hundreds of millions of years, and eventually mammals, returning to the sea just as reptiles had done before them, evolving into whales and dolphins and seals. Every giant begins, every tyrannosaurus, every triceratops, every towering sauropod that shook the earth with its footsteps started life as something that could fit in your hands, an egg. The journey from egg to adult is a story preserved in nests buried for millions of years, revealed in growth rings that mark each passing season like the pages of a diary no one was meant to read. Dinosaur eggs, when first discovered, baffled scientists. Some were enormous, the size of basketballs, thick-shelled and heavy. Others were surprisingly small, barely larger than a chicken's egg, despite coming from animals that would grow to massive size. The shell texture varied wildly, some rough and pebbled, others smooth and glossy. Each species laid eggs suited to their nesting strategy, their environment, the way they cared for their young, or left them to fend for themselves. The eggs were not scattered randomly. Dinosaurs built nests. Some dug shallow scrapes in sand or soil, circular depressions where eggs could be arranged in careful spirals or concentric rings. Others constructed mounded nests of vegetation, layering plant matter that would rot and generate heat. Natural incubators that kept eggs warm without constant parental presence. Still others returned to the same nesting grounds year after year, generation after generation, creating rookeries where hundreds of dinosaurs congregated to lay their eggs in relative safety. One of the most famous nesting sites lies in Montana, a place called Egg Mountain. There, in rocks from the late Cretaceous, paleontologists discovered the nests of Maiasaura, the good mother lizard. The nests were spaced precisely apart, each about 7 meters from its neighbors, just far enough that an adult could settle onto its nest without disturbing the neighbors. Within those nests lay eggs arranged in neat patterns and scattered among them, the bones of juveniles at various growth stages. This discovery revolutionized our understanding. Dinosaurs were not simply egg layers that abandoned their clutches. Some returned to feed their young, protected them, raised them through vulnerable early life stages. The hatchlings that emerged from those eggs were often tiny versions of their parents, but not always. Some species underwent dramatic changes in body proportions as they grew. A baby, Tyrannosaurus, was slender, long-legged, built more for speed than power, with a skull shaped differently from the bone-crushing monster it would become. Young sauropods had relatively short necks and tails, proportions that would elongate dramatically as they matured. Ceratopsians started life without the elaborate horns and frills that would define their adult appearance. How fast did they grow? For decades, this question remained unanswered. But dinosaur bones hold secrets that careful examination can reveal. Like trees, bones grow in layers, adding new tissue as the animal ages. When paleontologists slice a fossilized bone thin enough to examine under microscopes, they can count these growth rings, lines of arrested growth that mark periods when development slowed or paused, typically during seasons of scarce food or harsh weather. Each line represents roughly 1 year, a birthday marked in calcium and phosphate, preserved across millions of years. The growth rings tell remarkable stories. Large dinosaurs grew fast, astonishingly fast compared to modern reptiles. A baby sauropod might hatch weighing just a few pounds, small enough to hold in your arms. Within 5 years, that same individual could weigh several tons. Within 20 years, it might reach 30 or 40 tons. The growth rate was exponential in youth, slowing as the animal approached adult size, but never stopping entirely. Even the largest sauropods continued adding mass throughout their lives, though the pace diminished with age. Tyrannosaurus growth curves show a similar pattern. Young tyrannosaurs grew relatively slowly for their first decade or so, adding perhaps 30 to 50 pounds per year, gangly adolescents filling a different ecological role than their massive parents. Then, around age 14 or 15, they hit a growth spurt that rivaled anything seen in modern animals. For 4 or 5 years, they might gain 1,500 to 2,000 pounds annually, their bones thickening, their skulls broadening, their bodies transforming into the apex predators we recognize. By age 20, growth slowed again, and they had reached or nearly reached adult size. This rapid growth required enormous amounts of food. Growing dinosaurs were eating machines, consuming whatever they could catch or graze, converting vegetation or meat into bone and muscle at rates that demanded constant feeding. Parents that cared for their young would have been under tremendous pressure to provide food. Evidence from some nesting sites shows worn areas around nests where adults repeatedly came and went, paths trampled by countless trips delivering food to hungry mouths. But not all species provided such care. Some dinosaurs laid their eggs and departed, leaving the hatchlings to survive on instinct alone. These species typically produced many eggs, betting on quantity over quality, knowing that predators and harsh conditions would claim most of the young before they reached maturity. The babies that did survive were the quickest, the luckiest, the ones that learned fastest which plants were edible, where predators lurked, how to find water and shelter. The vulnerable period of youth lasted years for large species, sometimes a decade or more, before they grew large enough to be relatively safe from predators. During this time, juvenile dinosaurs occupied different ecological niches than adults. Young tyrannosaurs, too small to hunt large prey, likely chased smaller animals, competing more with other mid-sized predators than with their own parents. Young sauropods, unable to reach high branches, browsed lower vegetation, staying in denser cover where their small size offered some protection. Some species showed evidence of creche behavior, juveniles grouping together in herds separate from adults, finding safety in numbers. Trackways preserved in stone occasionally capture these moments, dozens of small footprints moving together, all the same size, all heading in the same direction. A snapshot of young dinosaurs traveling in a group. Whether adults supervise these groups or the juveniles banded together on their own remains unclear, but the strategy makes sense. Many eyes watch for danger. Many bodies confuse predators choosing a target. As dinosaurs aged, their bodies changed in ways beyond simple size increase. Bone texture shifted from porous and fast-growing in youth to denser and more compact in maturity. Hormones triggered the development of display structures, those horns, frills, crests, and spikes that distinguished species and sexes. In some dinosaurs, males and females looked remarkably different. Once mature, sexual dimorphism that complicated early paleontology before scientists understood they were seeing two sexes of the same species rather than separate species entirely. How long did dinosaurs live? The answer varies by species, by size, by lifestyle. Growth rings suggest that the very largest sauropods could live for 50, 70, perhaps even 100 years or more. Though reaching such ages was likely rare, predators faced constant danger from injuries, infections, and rival predators, factors that probably kept average lifespans shorter than their maximum potential. Studies of tyrannosaur populations suggest most died before age 30, though a fortunate few might have lived into their 40s. Smaller dinosaurs, facing more predators and higher metabolisms, likely lived correspondingly shorter lives, perhaps 10 to 20 years, for mid-sized species. Death came in many forms. Injury was common. Healed fractures appear in fossil bones with remarkable frequency. Breaks that mended while the animal lived, but surely caused pain and reduced mobility during healing. Infections from bites or wounds could fester and kill. Parasites burrowed into bone, leaving telltale holes and lesions. Old age brought arthritis, worn teeth, weakened bones prone to fracture. Some dinosaurs starved when they could no longer hunt or feed efficiently. Others fell to predators when age slowed their reflexes or weakened their defenses. But before death came life, and much of that life was spent growing. Juvenile fossils are rarer than adults because small bones are more fragile, more likely to be scattered by scavengers, destroyed by weathering, overlooked by fossilization processes that favor larger, more robust remains. Each juvenile fossil is therefore precious, a window into a stage of life less commonly preserved, evidence of the vulnerability, the transformation, the incremental journey from tiny hatchling to dominant giant. Some of the most poignant fossils capture dinosaurs who never completed that journey. A nest of Protoceratops hatchlings buried together by a sandstorm, their tiny skeletons still arranged in a circle, their lives ended before they had truly begun. A young Psittacosaurus preserved with more than 30 juveniles nearby, possibly a creche caught by volcanic disaster, adult and young entombed together in ash that hardened into their grave. For those that did survive, maturity brought new challenges and opportunities. Mating required finding partners, competing with rivals, performing displays that advertised fitness and health. Some species likely engaged in combat, males clashing with horns or headbutting to establish dominance. Others may have danced, called, or showed off colorful displays. Once mating succeeded, the cycle began again. Eggs laid in nests, a new generation preparing to hatch, to grow, to face the same obstacles their parents had overcome. Close your eyes and imagine standing in a Cretaceous forest at dawn. The air is thick and warm, heavy with moisture from the nearby sea. Light filters through canopy branches laden with leaves unlike any that exist today. You know what this world looked like, at least in outline. The fossils have told us about the plants, the landscape, the creatures that moved through it. But there is something missing from every reconstruction, every museum display, every artistic rendering of the Mesozoic world. Something essential, yet unknowable, or nearly so. Sound. What did the age of dinosaurs sound like? What calls echoed through those ancient forests? What bellows carried across the floodplains where herds migrated? What warning cries pierced the air when predators approached? The dinosaurs left us their bones, their footprints, their eggs and nests. But they did not leave us their voices. Sound is vibration, ephemeral by nature, gone the instant it travels beyond hearing range, leaving nothing behind that can fossilize, no trace that can be recovered from stone 75 million years later. Or so it seemed. But science, persistent and creative, has found ways to glimpse even this most fleeting aspect of dinosaur life. Not through direct evidence, for none exists, but through inference, through comparative anatomy, through computer modeling, through the study of what remains and careful extrapolation about what has vanished. The silence of the fossil record can be filled, at least partially, with educated guesses grounded in biology and physics, in the study of modern animals, and the structures they use to produce sound. The first challenge is that vocal organs rarely fossilize. Soft tissue generally decays before mineralization can preserve it. and the structures involved in sound production, larynxes and syrinxes, vocal cords and resonating chambers, are composed of cartilage and membrane, materials that disintegrate quickly after death. In thousands of dinosaur fossils discovered across nearly 2 centuries of paleontology, not one has preserved a larynx or syrinx in a form that would tell us definitively how the animal produced sound. But absence of direct evidence does not mean absence of clues. Dinosaurs were archosaurs, a group that today includes crocodilians and birds, both of which produce sound, though in very different ways. Crocodilians have larynxes and produce sounds through vibration of vocal cords, creating the deep bellows and hisses we associate with alligators and crocodiles. Birds have syrinxes, specialized organs located not in the throat, but deeper in the chest where the trachea splits into bronchi, allowing complex vocalizations and, in some species, the ability to produce two different notes simultaneously. Which system did dinosaurs use? The answer likely depends on the lineage. Non-avian dinosaurs, more distantly related to birds, may have possessed structures more similar to crocodilian larynxes, capable of producing sound, but perhaps not the complex vocalizations of birds. Theropods, especially those closest to the bird lineage, may have developed early syrinxes or transitional structures, precursors to the sophisticated vocal organs of modern birds. Without soft tissue preservation, we can only infer from phylogeny and from structures that did fossilize. Some dinosaurs, remarkably, left us the architecture of their sound production, even if the soft tissues themselves are gone. The hadrosaurs, those duck-billed herbivores that roamed late Cretaceous landscapes in vast herds, developed elaborate crests extending from their skulls, bony structures hollow inside, connected to the nasal passages through complex pathways that looped and curved before reaching the nostrils. For decades after their discovery, scientists debated the purpose of these crests. Enhanced sense of smell, visual display, thermoregulation. The answer, revealed through careful study and computer modeling, is sound. The hollow crests were resonating chambers, natural musical instruments built into the skull. When a hadrosaur exhaled through its nostrils, air passing through these chambers would vibrate at specific frequencies determined by the shape and length of the passages. Different species had differently shaped crests, tubes, and chambers of varying dimensions, meaning each species would have produced distinctive calls, unique acoustic signatures that allowed individuals to identify their own kind across distance. Scientists have created digital models of these crest structures, mapping the internal passages with CT scans, then simulating airflow through them to predict the frequencies produced. The results are haunting. Deep, resonant tones, something between a foghorn and a woodwind instrument, notes that would have carried for miles across open landscapes. Parasaurolophus, with its long, backward-curving crest, produced low-frequency calls around 30 to 70 hertz, sounds felt as much as heard, vibrations that would have traveled through the ground as well as the air. Imagine a herd of Parasaurolophus at sunset, dozens of individuals calling to each other as they settled for the night, each one adding its voice to a chorus of deep, mournful notes that rolled across the floodplain like distant thunder. The young would have higher-pitched calls, their crests not fully developed, their resonating chambers shorter, and producing different frequencies. Adults could have identified juveniles by sound alone, and within that chorus, parents might have recognized their own offspring's voices. The slight variations that made each call unique, despite belonging to the same species. Other hadrosaurs had different crests and therefore different calls. Corythosaurus had a rounded, helmet-like crest that would have produced higher, more trumpet-like sounds. Lambeosaurus had a crest with a forward, pointing spike that added complexity to the resonating chamber, possibly allowing different tones or even multiple notes simultaneously. The diversity of crest shapes may have evolved partly through sexual selection. Individuals with more impressive calls attracting more mates, driving the evolution of increasingly elaborate sound-producing structures. But hadrosaurs were not the only dinosaurs making noise. Ceratopsians, though lacking hollow crests, possessed large frills and powerful jaw muscles, structures that could have been used to produce sounds through other means. Modern animals demonstrate many ways to create noise without sophisticated vocal organs. Rabbits thump their feet as warning signals. Gorillas beat their chests. Crocodiles create infrasound by vibrating their bodies against the water's surface. Ceratopsians may have clapped their jaws together, creating sharp cracks that served as alarm calls or threat displays. They may have scraped their horns against trees or rocks, producing sounds that advertised their presence or challenged rivals. Sauropods, the giants whose footsteps shook the earth, likely produced some of the most impressive sounds in the Mesozoic world. Their sheer size meant their vocal cords, if they possessed them, would have been enormous, capable of creating extremely low-frequency sounds, infrasound below the range of human hearing. Elephants produce infrasound that travels for miles, allowing herds to communicate across distances far greater than visual range allows. Whales use similar low-frequency calls to communicate across entire ocean basins. A 70-ton Argentinosaurus, with a neck longer than most buildings are tall, could have produced calls of such low frequency and high amplitude that they traveled for dozens of miles. Felt by other sauropods through specialized organs sensitive to vibration. These calls might have coordinated migrations, warned of predators, or helped individuals locate their herds when separated. The sound would have been less like a roar and more like distant rolling thunder, a rumble felt in the chest and bones, a vibration that announced the presence of something immense moving through the landscape. Theropods, the predators, present a different puzzle. Movies have given them mighty roars, especially Tyrannosaurus, whose roar in Jurassic Park became iconic. But the roar of a lion is produced by vocal cords that vibrate in specific ways, creating the characteristic sound that carries across the savanna. Did tyrannosaurs possess similar structures? Could they actually roar? The evidence suggests probably not, at least not in the way mammals roar. Birds, the living descendants of theropods, do not roar. They chirp, sing, squawk, screech, but even the largest birds produce sounds fundamentally different from mammalian roars. The cassowary, one of the largest and most dangerous birds alive, produces deep booming sounds, rumbles and thuds that carry through dense forest, but it does not roar. The closest living relatives to dinosaurs, crocodilians, produce bellows and hisses, intimidating but not the sharp, piercing roars of big cats. More likely, Large theropods produced sounds through closed mouth vocalizations, rumbles and booms generated deep in the chest or throat, expelled through closed or barely opened jaws. These sounds would have been felt as much as heard, low frequency vibrations that intimidated rivals and warned prey without the high pitched quality of a roar. Some modern birds produce such sounds, cassowaries and emus creating deep drumming noises that resonate in their bodies before being released. Tyrannosaurus may have done something similar, its massive chest cavity acting as a resonating chamber, producing sounds that carried weight and menace, even if they lacked the sharp crack of a lion's roar. Smaller theropods may have been more vocal in the traditional sense. Velociraptors and their relatives were bird-like in many ways, possessed large brains and complex social behaviors that likely included communication through sound. They may have chirped and squawked like modern ravens or crows, intelligent birds that use varied vocalizations to coordinate pack hunting, warn of danger, and communicate complex information to each other. A pack of velociraptors coordinating an attack might have filled the air with sharp staccato calls, individuals signaling to each other, adjusting strategy through sound. The soundscape of the Mesozoic would have varied by location and time. Near coastlines, the calls of pterosaurs would have mingled with the sounds of waves and marine reptiles surfacing to breathe. In dense forests, the air would have been thick with insect buzzing, a sound fundamentally unchanged for hundreds of millions of years, overlaid with the calls of small dinosaurs moving through undergrowth, the rustle of feathers, the snap of twigs under clawed feet. On open plains, the distance-carrying calls of hadrosaur herds and sauropod rumbles would have dominated, punctuated by the warning cries of herbivores spotting predators. At night, the soundscape would have shifted. Diurnal dinosaurs would have fallen silent, settling into sleep or quiet rest. But nocturnal species, smaller dinosaurs, and early mammals would have emerged, their own vocalizations filling the darkness. The Mesozoic night may have been surprisingly quiet compared to modern tropical nights thick with frog calls and insect choruses, since many of those modern sound makers had not yet evolved or were restricted to different habitats, but it would not have been silent. Life always makes noise. Movement always creates sound. Even breath is audible in stillness. Computer models continue to refine our understanding of these vanished voices. As scanning technology improves, as more complete skulls are discovered with internal structures preserved, as our understanding of sound production in modern animals deepens, the models become more sophisticated, more accurate, more capable of reconstructing not just pitch, but timbre, resonance, the quality of sound that makes each voice distinctive. Labs can now 3D print replicas of hadrosaur crests, blow air through them, and actually hear approximations of calls that last echoed 75 million years ago. The results are humbling and beautiful. These were real sounds, produced by real animals in real environments. Hearing them, even as reconstructions, bridges the gap between fossil and living creature in ways visual reconstructions alone cannot. Sound is immediate. It exists in time, not space. It unfolds as you listen, creating an experience rather than an image. To hear the call of Parasaurolophus, even digitally recreated, is to experience something of what it was like to be present in that world, to stand on that plain at sunset, and hear the voices of creatures now gone. And yet, we must remain humble about the limits of our knowledge. These reconstructions are educated guesses, inferences based on structure and comparison. The actual sounds may have been subtly or dramatically different from our models. Soft tissue we cannot see may have modified sound production in ways we cannot predict. Behaviors we cannot infer may have created sounds through mechanisms we have not considered. The soundscape we imagine is at best an approximation, a sketch rather than a recording. But it is something. It is better than silence. It gives voice, however uncertain, to creatures that have been voiceless for tens of millions of years. For 165 million years, the age of dinosaurs had endured. Empires of scales and bone, bloodlines stretching back through the Jurassic, through the Triassic, into the deep shadows of prehistory. Dinosaurs had survived climate shifts, rising and falling seas, the breakup of supercontinents, volcanic eruptions that darkened skies for decades. They had weathered smaller extinctions, adapted to changing vegetation, evolved alongside flowering plants and the insects that pollinated them. They were not fragile. They were not struggling. On the last day of the Cretaceous period, 66 million years ago, dinosaurs ruled the Earth as completely as they ever had. And then the sky caught fire. The morning began like any other in the late Cretaceous. The sun rose over forests thick with magnolias and ferns. Herds of triceratops grazed in upland regions, their three-horned faces lowering to crop vegetation, their frilled heads turning occasionally to scan for threats. Edmontosaurus moved in larger groups through river valleys, hadrosaurs whose duck-like bills stripped leaves from branches. In the forests, smaller dinosaurs hunted and foraged. Overhead, pterosaurs glided on morning thermals, searching for fish in rivers that wound through a landscape far different from today's, though recognizable in its fundamental forms. Trees, water, earth, sky. Somewhere in what would one day be Mexico's Yucatan Peninsula, something moved through the darkness beyond the atmosphere. An asteroid, perhaps 6 to 10 miles wide, a mountain of rock and metal, traveling at 45,000 miles per hour, falling toward Earth on a trajectory that had been set millions of years earlier. No dinosaur looked up and saw it coming. No creature had any warning of what approached. The asteroid crossed the boundary between space and air, began to compress the atmosphere before it, to glow with heat from friction, to become a meteor brighter than 1,000 suns. It struck the shallow sea off the coast with energy beyond comprehension. The impact released the equivalent of 10 billion atomic bombs detonating simultaneously. The asteroid vaporized instantly, along with trillions of tons of rock, water, and any living thing within hundreds of miles. A crater began forming, expanding outward and downward, rock behaving like liquid under the impossible forces involved. The seafloor was punctured. The crust was breached. In seconds, a crater 20 miles deep and more than 100 miles wide was blasted into the earth. The explosion sent a pressure wave radiating outward faster than sound, flattening everything in its path. Trees were ripped from the ground and shredded. Animals were killed instantly by the shock wave alone, their bodies thrown for miles before the fire even reached them. The impact threw millions of tons of vaporized rock upward, out of the atmosphere entirely, into space, where it spread in a growing cloud that would eventually encircle the planet. Within minutes, tsunamis hundreds of feet tall radiated outward from the impact site, racing across the shallow seas that covered much of the continents. These waves crashed inland for hundreds of miles, drowning forests, scouring landscapes, carrying marine sediments far into the interior. The wall of water reshaped coastlines, deposited layers of debris that would remain as evidence 66 million years later, a marker line in the geological record marking before and after, the boundary between the Cretaceous and the beginning of the Paleogene. But the tsunamis were only the beginning. The vaporized rock that had been thrown into space began to fall back. Millions upon millions of molten droplets re-entering the atmosphere, each one glowing, radiating heat, collectively raising the temperature of the entire atmosphere. For creatures far from the impact, who had survived the initial shockwave, who stood confused and frightened by sounds and tremors beyond their experience, the sky began to glow red, then orange, then white hot as the air itself became an oven. Global wildfires ignited simultaneously across the planet. Forests that had stood for millions of years burst into flame. Animals caught in the open had nowhere to hide. The heat pulse lasted for hours, roasting the surface of the earth, turning vast regions into infernos. Those that survived did so by being underground, underwater, or sheltered in caves and burrows where rock and earth provided insulation from the thermal pulse that baked the surface world. The fires consumed continents. Smoke and ash poured into the atmosphere, joining the dust from the impact itself. Within days, the sky darkened. Within weeks, the sun was barely visible, a dim disk behind clouds of debris that encircled the globe. Temperatures that had spiked during the thermal pulse now plummeted as sunlight was blocked. The world entered an impact winter, darkness and cold settling over landscapes still smoldering from the fires. Photosynthesis stopped. Plants died. First the smaller species, then the shrubs, and finally even the trees that might have survived began to starve without light. The food chain collapsed from the bottom up. Herbivores that had survived the initial catastrophe found nothing to eat. They starved within weeks or months, their bodies adding to the mass death that littered the landscape. Predators held on longer, feeding on the abundant carrion. But as that resource was exhausted, and no new prey reproduced to replace it, they too began to die. The oceans fared little better. The impact had acidified seawater, killing plankton, the microscopic organisms that formed the base of marine food webs. Ammonites, which had thrived for hundreds of millions of years, went extinct. Most marine reptiles vanished. Coral reefs died globally. The oceans became graveyards, their waters dark and lifeless, stirred only by the remnant tsunamis still echoing around ocean basins days and weeks after the initial impact. Dinosaurs, which had dominated terrestrial ecosystems for so long, found themselves utterly unprepared for this catastrophe. Large herbivores needed enormous amounts of food that no longer existed. Sauropods, if any still survived into the latest Cretaceous, would have been among the first to starve. Ceratopsians, hadrosaurs, the great herds that had migrated across continents following seasonal vegetation, found only ash and frozen ground. They died where they stood, unable to flee, unable to adapt, their size becoming a liability when resources vanished. Predators lasted longer, but suffered their own fate. Tyrannosaurus, the apex predator of North America, likely scavenged the dead at first, its powerful jaws capable of crushing bones to access marrow, its metabolism slow enough to survive short-term starvation. But as the carrion was consumed or rotted, as cold preserved some carcasses but made them frozen and inaccessible, even the great predators began to succumb. Cold-blooded or warm-blooded, it did not matter. Without food, without sun, without heat, the largest terrestrial animals could not survive. Smaller dinosaurs might have lasted longer. Those that could burrow, that ate seeds or insects, that required less food and could shelter underground during the worst of the impact winter. But the darkness persisted for months, perhaps a year or more. The cold deepened. Acid rain fell from skies heavy with sulfur compounds. Whatever plants began to recover from seed banks were poisoned by contaminated soil or killed by late frosts in regions that had never before known ice. And yet, the extinction was selective. Not everything died. Small mammals survived, burrowing creatures that could hibernate, that ate seeds and nuts cached before the disaster, that required little food and could wait out the darkness. Birds survived, or at least some lineages did. Small bodies, diverse diets, ability to fly, to find food sources, perhaps nesting in burrows or caves. These advantages carried them through. Crocodilians survived, cold-blooded and capable of going months without eating, hunkered in rivers and swamps where some aquatic life persisted. Turtles, lizards, salamanders, small survivors that could hide, wait, endure. But of the non-avian dinosaurs, not one species survived. Not a single tyrannosaur, ceratopsian, hadrosaur, or sauropod made it through the bottleneck. The largest animals on land were eliminated completely. An entire ecological tier was removed. For the first time in 165 million years, the world had no dinosaurs larger than a turkey. The age of giants had ended in darkness and fire, in starvation and cold, in a catastrophe so complete that it reshaped the entire trajectory of life on Earth. The impact at Chicxulub, now buried under limestone in Mexico's Yucatan, left a scar 110 miles wide. Drilling projects have recovered rock from the crater's depths, material that shows the signatures of extreme shock, of instantaneous melting, of forces that reorganized crystal structures in ways only seen in atomic explosions and asteroid impacts. The timing aligns perfectly with the extinction. The layer of iridium, an element rare on Earth but common in asteroids, marks the boundary worldwide, a thin line of extraterrestrial dust mixed with the ash of burning continents. But the asteroid was not alone in its destruction. Across the globe, in what is now India, massive volcanic eruptions were already underway. The Deccan Traps, vast flood basalt eruptions that would eventually cover an area larger than France in lava thousands of feet thick. These eruptions had begun before the impact and continued for hundreds of thousands of years after, releasing carbon dioxide, sulfur, and other gases that warmed the planet after the initial impact. Winter faded, creating instability, preventing full recovery, adding stress upon stress to ecosystems already devastated. Some scientists argue the volcanism alone might have caused the extinction eventually. Others maintain the impact was the decisive blow. Most now believe it was the combination, the 1-2 punch of catastrophes that left no room for large animals to adapt. The volcanic eruptions had been weakening ecosystems for millennia before the asteroid arrived. Species were already stressed, climates already unstable. The impact simply finished what the volcanoes had begun. When the skies finally cleared, perhaps a year or two after impact, perhaps longer, the world that emerged was transformed beyond recognition. The dinosaurs were gone. The pterosaurs had vanished. Marine reptiles had disappeared from the oceans. 75% of all species on Earth were extinct. But life, as it always does, began to recover. The surviving mammals emerged from their burrows into a world empty of the predators and competitors that had kept them small and nocturnal for 100 million years. They began to diversify, to grow larger. Birds, the only dinosaurs to survive, spread across the continents. They too began to diversify. Though they would never again reach the sizes of their non-avian cousins, never again produce giants like the dinosaurs. The largest birds that would ever evolve, the terror birds of the Cenozoic, the moas of New Zealand, were impressive but small compared to Tyrannosaurus. Tiny compared to the great sauropods. The age of mammals had begun, an age that continues today, an age that would eventually produce primates, hominids, and ultimately humans who would dig into ancient stone and discover the bones of the vanished giants, who would reconstruct their forms, study their lives, marvel at their existence, and wonder at their ending. The dinosaurs have been extinct for 66 million years, yet they have never been more alive in human consciousness. They fill our museums and our movies, our children's books and our scientific journals, our imaginations and our nightmares. They are perhaps the only extinct animals that nearly everyone can name, that cross boundaries of age and culture, that inspire equal fascination in a 5-year-old child and a Nobel laureate. This strange persistence, this refusal to be forgotten, tells us something profound about both dinosaurs and ourselves. The story of this cultural presence begins in the 19th century, with fragments of bone weathering out of English hillsides. Before then, people occasionally found large fossilized bones and attributed them to giants, dragons, monsters from ancient myths. The bones fit existing stories, confirming what people already believed about a world once populated by creatures larger and stranger than those alive today. But in the 1820s, scientists began to realize these bones belonged to something else entirely, to reptiles of impossible size, to creatures that did not fit into any existing category. The word dinosaur was coined in 1842 by Richard Owen, meaning terrible lizard, though they were neither particularly terrible nor truly lizards in the modern sense. That name, dramatic and evocative, caught the public imagination immediately. Here were real monsters, not from myth, but from actual history. Creatures that had walked the earth, not in legend, but in fact. The discovery thrilled the Victorian public, hungry for wonders, in an age of scientific revelation. Dinosaurs became celebrities before their skeletons were even fully assembled. The first dinosaur sculptures, created by Benjamin Waterhouse Hawkins for the Crystal Palace exhibition in London in 1854, showed ponderous reptilian beasts, quadrupedal and sluggish, imagined as oversized lizards basking in primordial swamps. These reconstructions were inaccurate by modern standards, but they represented the best understanding available at the time. They were also immediately popular, drawing crowds who had never seen anything like them, who marveled at the size and strangeness of creatures proved by science to have actually existed. As more fossils emerged, the reconstructions changed. The discovery of complete skeletons showed that many dinosaurs walked on two legs, not four, that they were more active than initially supposed, more varied in form and habit. Museums began mounting skeletons, creating displays that allowed visitors to stand beneath towering bones and feel their own smallness in the presence of ancient giants. These displays were transformative. To see a dinosaur skeleton is to experience a kind of time travel, to confront physical evidence of deep time, to stand in the presence of something that should not exist, yet undeniably did. Children were drawn to dinosaurs with an intensity that puzzled adults. Perhaps it was the combination of factors: real, yet extinct; terrifying, yet safely distant; enormous, yet comprehensible; monstrous, yet scientifically validated. Dinosaurs occupied a perfect space in childhood imagination. Dragons that had actually existed, monsters whose reality was confirmed by the authority of museums and scientists. Learning their names, often impossibly long and Latin-derived, became a badge of knowledge, a way for children to demonstrate mastery over complexity, to own something powerful through the act of naming and understanding. The 20th century amplified this fascination through popular culture. Early films like The Lost World in 1925 and King Kong in 1933 brought dinosaurs to cinematic life, using stop-motion animation to show them moving, hunting, fighting. The effects were primitive by modern standards, but revolutionary for their time, creating moving images of creatures no human had ever seen alive. These films established dinosaurs as staples of adventure and science fiction, as obstacles to overcome, as symbols of nature's power and humanity's vulnerability. Literature embraced them too. Arthur Conan Doyle's The Lost World imagined an isolated plateau where dinosaurs still survived, mixing adventure with scientific speculation. Later writers used dinosaurs as metaphors, as symbols of obsolescence or of nature's indifference to human concerns, as reminders that dominance is temporary and extinction is patient. Ray Bradbury's A Sound of Thunder used time-traveling dinosaur hunters to explore chaos theory and the fragility of causality. Countless children's books taught basic concepts of evolution, extinction, and deep time through the accessible medium of dinosaur stories. But nothing prepared popular culture for the impact of Jurassic Park in 1993. Steven Spielberg's film, based on Michael Crichton's novel, combined cutting-edge special effects with scientific consultation to create dinosaurs more realistic than anything previously seen. The Tyrannosaurus attacking the vehicles in the rain, the velociraptors hunting in the kitchen, the Brachiosaurus rising on its hind legs to feed from trees. These images seared themselves into global consciousness. The film earned nearly $1 billion worldwide and sparked a dinosaur renaissance in popular culture that continues 3 decades later. What made Jurassic Park revolutionary was not just the effects, but the portrayal of dinosaurs as active, intelligent, bird-like creatures rather than lumbering reptiles. The film incorporated then recent scientific findings, showing dinosaurs as dynamic and complex. It also raised genuine scientific questions about extinction, preservation, genetics, and the ethics of resurrection that scientists were actually beginning to explore. The line between entertainment and education blurred. Children who saw the film became paleontologists. Scientists found their funding increased as public interest surged. The franchise that followed, spanning multiple films across 30 years, has had mixed scientific accuracy, sometimes incorporating new discoveries, sometimes ignoring them for dramatic effect. But the cultural impact remains enormous. Dinosaurs became more than museum exhibits or textbook illustrations. They became characters with personality, threats with intelligence, creatures that could be imagined as living animals rather than just bones and stone. The films kept dinosaurs at the forefront of popular consciousness, ensuring each new generation encountered them not as dusty relics, but as vivid, thrilling possibilities. Beyond entertainment, dinosaurs have become tools for education in ways their discoverers never imagined. They teach evolution by showing how species changed over millions of years, how small theropods gave rise to birds, how body plans adapted to different ecological niches. They teach extinction by demonstrating that dominance is temporary, that even the most successful life forms can vanish. That survival depends on adaptability and sometimes simple luck. They teach deep time by forcing minds to grapple with millions and hundreds of millions of years, timescales that dwarf human history but are essential to understanding Earth itself. In classrooms worldwide, dinosaurs serve as entry points to broader scientific concepts. A child fascinated by Tyrannosaurus learns about predator-prey relationships, biomechanics, comparative anatomy. A child captivated by Triceratops learns about herbivore defenses, sexual selection, growth and development. The names may be difficult, but children learn them eagerly. And in learning them, they learn that science is not always simple, that complexity can be mastered, that knowledge is something worth pursuing. Museums have evolved to meet this interest. Modern dinosaur halls are not just collections of bones, but immersive experiences, with lighting designed to dramatic effect, sound effects suggesting ancient environments, interactive displays explaining fossilization and excavation, video screens showing reconstructions of behavior based on the latest research. Some museums create life-sized animatronic dinosaurs that move and roar, bringing a tactile immediacy to creatures otherwise knowable only through fossils. The line between education and entertainment blurs deliberately, recognizing that engagement drives learning. Scientific research has accelerated in tandem with public interest. Funding for paleontology, often precarious, improves when the public cares about discoveries. New finds make headlines. Announcements of feathered dinosaurs, of dinosaur colors reconstructed from melanosums, of soft tissue preservation in Tyrannosaurus. These stories reach far beyond scientific journals into mainstream news, capturing public imagination and justifying continued investment in research that might otherwise seem impractical. The questions scientists ask have also evolved. Early paleontology focused on identification and classification, on naming species and determining relationships. Modern paleontology asks behavioral questions. How did they move? What did they eat? How did they raise young? Did they migrate? How did they communicate? These questions require interdisciplinary approaches, combining paleontology with biomechanics, chemistry, computer modeling, comparative biology. Dinosaurs have become testing grounds for methods that illuminate not just the past, but the present. Techniques applicable to understanding modern ecosystems, extinction risks, climate change. Technology continues to transform the field. Drones survey fossil sites from above, identifying promising locations without disturbing the ground. 3D scanning creates perfect digital copies of fossils that can be shared worldwide, studied by researchers who never touch the original, printed as replicas for museums that cannot afford real specimens. Machine learning algorithms analyze bone structure, identifying patterns invisible to human observation, predicting soft tissue arrangements with increasing accuracy. Virtual reality allows people to walk among dinosaurs, to experience size and scale in ways static displays cannot convey. Artists have become crucial collaborators in paleontology. Paleoart, the reconstruction of extinct animals in paintings and sculptures, is not mere illustration, but an interpretive science requiring deep knowledge of anatomy, biomechanics, behavior, and ecology. The best paleo artists work closely with scientists, translating fossil evidence into visual form, making educated guesses where evidence is incomplete, creating images that become the default visualization of species in the public mind. These reconstructions evolve as knowledge improves, older images replaced by newer ones that incorporate feathers, correct postures, updated color schemes based on fossil evidence. Dinosaurs have also become symbols in broader cultural conversations. They represent extinction in climate change discussions, reminders that even dominant species can vanish if conditions change too rapidly. They represent the power of science to recover lost knowledge, to read messages written in stone, to reconstruct worlds from fragments. They represent childhood wonder preserved into adulthood, the ability to remain curious, to ask questions, to marvel at the strangeness and diversity of life across time. In an age of rapid environmental change and documented modern extinction events, dinosaurs carry cautionary weight. They succeeded for 165 million years, far longer than mammals have dominated the Earth. Yet an unpredictable catastrophe ended them. Their story suggests that success is no guarantee of survival, that the future is uncertain, that stewardship matters because dominance can evaporate in geological instants. This lesson resonates as humans confront their own impact on global ecosystems as species vanish at rates not seen since the end of the Cretaceous. Yet dinosaurs also inspire optimism. Life recovered after their extinction. New forms arose. Ecosystems rebuilt themselves. the planet endured and diversified and thrived again, demonstrating resilience even after catastrophe. The birds that sing outside your window are living dinosaurs, descendants of creatures that survived the asteroid, adapted to changed conditions, and flourished into more than 10,000 species. Life finds ways forward even through devastation. The story does not end with extinction. It continues, transforms, begins again. As research continues, as new fossils emerge from rock in Mongolia, China, Argentina, Antarctica, the story grows richer and stranger. Species discovered in the past decade include some with feathers arranged like modern birds, others with elaborate horns and frills for display, still others with body plans so unusual they challenge existing categories. Each discovery refines understanding, adds detail, forces revision of assumptions. The dinosaurs we imagine today would be barely recognizable to scientists from 50 years ago, and the dinosaurs imagined 50 years hence will likely differ from those we envision now. But certain truths remain constant. They existed. They dominated terrestrial ecosystems for epochs. They diversified into thousands of species, each adapted to specific niches, each representing millions of years of evolutionary refinement. They were not failures or dead ends, but among the most successful animals ever to walk the earth. Their extinction was catastrophic, but not inevitable, caused by coincidence and bad luck, rather than inherent weakness. And they persist in memory, in fossil, in descendant, in imagination, refusing to be forgotten despite 66 million years of absence. The relationship between humanity and dinosaurs is unique in the history of human engagement with the natural world. We never coexisted with them. We have no folk memories, no survival strategies developed over generations of interaction. Everything we know comes from inference, deduction, reconstruction. Yet they occupy outsized space in our culture, our education, our collective imagination. Perhaps because they represent something essential about the human desire to understand the past, to know what came before, to situate ourselves in the vast story of life on Earth. Perhaps because they combine the exotic and the comprehensible, strange enough to fascinate, but knowable enough to study. Perhaps because they prove that the world was once profoundly different, that change is constant, that the present is not permanent. Perhaps simply because they are magnificent. And magnificence calls to something deep in human nature, a desire to witness grandeur, to stand in awe before something greater than ourselves. Let the dinosaurs cradle your thoughts tonight as you drift towards sleep. Let their long, slow story unfold in the background of your mind, a reminder that time is deep, that change is constant, that the impossible becomes possible given enough millions of years. Let their bones speak from stone, their descendants sing from trees, their memory live in the wonder you feel when contemplating creatures so magnificent they barely seem real, yet undeniably were. The age of dinosaurs is over. They are gone, but not forgotten. Extinct, but still present. Vanished, but preserved in stone and descendant and imagination. They walked the earth for longer than we can truly comprehend, and they left marks that will never fully erode, echoes that will never completely fade, a legacy written in fossils waiting in darkness and in birds filling the sky with wings and song. Sleep now. Dream of ancient forests and creatures too large to believe. Dream of time measured in millions, of evolution's patient work, of life's endless creativity. Dream of a world both strange and familiar, both impossibly distant and intimately connected to the present. Dream of dinosaurs, those eternal giants, those vanished wonders, those creatures that dominated the earth and then released it, making space for everything that followed, including you, here now, drifting into sleep beneath the same stars that shone on their final evening, carrying their story forward simply by knowing it existed, by caring that it did. Good night.